This is problem number 13. An airplane flying at an altitude of 7 miles, and an airplane is flying at an altitude of 7 miles and passes directly over a radar antenna as shown in the figure. We're going to kind of embellish this figure a little bit here. When the plane is 10 miles from the antenna, the radar detects that the distance between the plane and the tower is changing at the rate of 300 miles per hour. What is the speed of the airplane at that moment? Okay, so one thing just to clarify, this is our antenna or our tower. They kind of call it two different things unless I typed it wrong, but certainly I typed it as two different things. Our antenna, our tower is right here. We have an airplane. It flew over the tower. Now they're talking about it 10 miles further down or 10 miles beyond the antenna. So somewhere over here, we're just going to call that, I know that doesn't look very good, we're going to call that the airplane. Okay. Then, very important in this, the airplane is flying at an altitude of 7 miles. And they don't mention anything about the plane going up higher in the air, down lower in the air, so that 7 miles is a constant. So when it flew over the tower, it was at 7 miles. And it's still now at 7 miles. So I can label that 7 miles in my picture. I don't need a variable for that. That is 7 miles. Throughout the whole problem, we're assuming that plane is flying at 7 miles because it says the plane is flying at an altitude of 7 miles and doesn't indicate anywhere else that that altitude is going to change. Okay, then, pass directly over radar antenna shown in the figure. When the plane is 10 miles from the antenna, how do you measure distance? You measure it in a straight line. So when the plane is 10 miles from the antenna, we would measure that distance that way. Let's label that S. And that we have to have as a variable because clearly that's going to change when the plane was over here. S was smaller. When the plane comes over here, S is certainly going to get bigger. So I can't label that 10. All right? The distance from the plane to the tower when it's 10 miles, so I can kind of make a note of that at some point, S will be 10. But I label that as a variable because S, that distance from the plane to the tower, is changing throughout the problem. The radar detects that the distance between the plane and the tower is changing at a rate of 300 miles per hour. Wait a minute, a rate of 300 miles per hour, that's a derivative, and it's the distance between the plane and the tower. Wait a minute, guys, that's S. From the plane up here, the tower, down here, that's S. So they just told us at a rate. So ds dt equals 300 miles per hour. All right, what is the speed of the airplane? Okay, speed of the airplane, we're talking about, it's not going up or down, so we're talking about the horizontal speed. So now we will introduce another variable. Let's call the horizontal distance x. And again, that's a variable because as you know, the plane flies, x changes. X is smaller. Here, at our indication right here at this point, x was 10, and it's going to keep going past the tower. So x will keep getting greater. So that's a variable. Okay, so it looks like we have our setup. What is the speed of the airplane? So our question is, could we please find our speed? That's a rate. Could we please find the x dt? Okay, I need some kind of equation that relates x and s. They drew the picture for us, or you look right here, and you're thinking of a right triangle. So you're thinking, hopefully, of the Pythagorean theorem. So let's write that out. I've got x squared. And again, x is a variable that changes throughout the problem. I've got 7 squared. 7 is a constant in this problem, so I can sum it in right away. And it's going to equal s squared. Let's take the derivative. And again, we're taking the derivative with respect to time. They wanted rates. So I take the derivative with respect to time. When I do that on the left side, I get 2x. I get dx dt. The 7 is a constant. 7 squared is 49. The derivative is 0. And the right side, I get 2s, and I get ds dt. Let's sub in. This problem does not look bad at all. Dx dt is what I'm looking for. Let's see. On the right side, I've got 2. How much is s? When s, now we can use this fact. We've taken the derivative. Now we can sub in. So s is 10. Ds dt is 300. Right side looks good. Dx dt is what I was looking for. I've got a 2. Oh, shoot. What is x? So I come back up here to my picture. I note I've got this right triangle. There it is. The right triangle, so I've got my Pythagorean theorem. I had it before. I used that equation I took the derivative of. X squared plus 7 squared equals 10 squared, because S is 10. 10 squared is 100, 7 squared is 49. Subtracting, I get x squared equals 51, or x is the positive square root of 51. So I can also sub in for x. I note that the 2's cancel out, and I solve this for dx dt, and I get dx dt equals, it looks like 3,000 over the square root of 51. Not a real meaningful number, so I'll pull up the calculator and let's see how fast that is. And always one thing that's kind of interesting to think about is the distance, bring it down so you can see it. My distance between the tower and the plane was 300. So would the plane be going faster or slower than 300? And let's just try this and see. I've got 3,000. I'll divide it by square root of 51. And let that kind of sink into your intuition for a little bit. So the speed of the plane is 420 miles per hour. And for an AP question, we keep 3 decimals, so I guess I need to be careful there. 420.084 miles per hour. So I've got the plane, I'll label that 420.084 miles per hour. So I've calculated the speed of the plane, completing the problem.